This podcast is about the trends on the periodic table for ionization energy. And ionization energy is the amount of energy that it takes to remove one electron from an atom, from the outermost electron that gets removed. And the units for ionization energy are energy units, so they're typically kilojoules or joules or megajoules, some sort of joules, usually kilojoules. Why does this require energy? Because we have to overcome the force of the pull of the nucleus, because the nucleus is positive and it's pulling on the electrons, and so removing that is always going to require energy. Ionization energy is related to chemical reactivity. So if an atom has a lower ionization energy, that means that electrons are removed more easily, and therefore the element is going to be more reactive. So often we'll describe reactivity in terms of ionization energy. Trends in ionization energy, they really fit the trends in size, so that as you go down a group, ionization energy decreases, which means it gets easier to remove the outer electron as the atom gets smaller, which makes sense. As the atom gets bigger, because as it gets larger going down a group, the electron is further away and it's easier to remove, so it's going to have a lower ionization energy. So the amount of energy is going to be quite a bit lower. Also notice going across the periodic table from left to right, the ionization energy is going up, increasing, and that's again, as the atoms get smaller, the ionization energy is going to increase, going to be harder to remove that outer electron going across a period. Decreasing, going down a group, increasing, going across a period on the periodic table. So atoms that have lots of electrons can lose more than one electron. The first ionization energy is the energy to remove the first electron. So that would be the outermost electron from a neutral atom. And here's a diagram or picture of what happens there. So element X loses an electron and becomes a cation. So this process would be what we would describe as the first ionization energy. The second ionization energy is the energy required to remove a second electron. So it's already lost one, so it's already a cation. We're going to remove another electron, and now the atom is going to have a +2 charge because it's lost its second electron. And you could, and then keep losing electrons. You could have the third ionization energy, the fourth, the fifth, go on, until all the electrons are gone. This table is a description of the successive ionization energies for elements lithium through sodium. So here's lithium, atomic number 3, and then sodium is down here, atomic number of 11. So they are the elements in the second period of the periodic table. And so if we look at lithium, which only has 3 electrons, it only has 1 valence electrons, 3 total electrons. The first ionization energy costs a little bit of energy. The second one is going to cost a lot more, and then more still. We look at nitrogen, which has 7 total electrons, 5 valence electrons. The first electron, 1.4, the next one, 2.86, 4.58, 7.48. So it always is higher and higher amounts of energy to remove one more electron. We're going to use this table when we refer back to this table, the next page. We're going to go into detail what happens with boron here. So the numbers on the next page come from the boron row in this table. So it turns out that there's a really big difference between the energy required to remove the outer electrons, or the valence electrons, and the amount of energy required to lose the inner electrons. So we're going to use boron as an example and go over it in detail. The electron configuration for boron, plain old boron, is 1s2, 2s2, 2p1. When the first electron gets removed, it's going to come out of the highest energy, which is the 2p, and that's the one that's going to go. So if we look on the chart, we see that the IE1, or the first ionization energy, the one to remove the first electron, the last electron in, is going to be 0.8 megajoules per mole. And that's going to leave us with this electron configuration. So now we have boron with a +1 charge. It has lost one electron, 1s2 and 2s2. So now it has 4 electrons left. And now we're going to remove another one, and it's going to come out of the 2s orbital. Okay, second ionization energy is 2.43, so it costs a little bit more energy. Remember, we've made the cation, so it's gotten smaller, so everything's closer to the nucleus, harder to pull off that second electron, costs you a little bit more energy, and now we have 2s1. Going to do it again. Take off a third electron. Again, it's going to cost you a little bit more energy, 3.66. Now both electrons from the 2s are gone. They've both been removed. We've lost 3 electrons total. And now we're left with 1s2. But remember that this 1s2 electrons, if we look back at the beginning, these were my inner electrons to start with. There's either the shielding, filled up, inner, closed, we call them closed shell because they've been filled. So now, if we want to remove an electron, it's like all the easy ones have been taken, and now we have to remove an electron that's from an energy level that's filled, and they do not want to let go, so it's going to cost a lot more energy. So the fourth ionization energy is 25.02, so a lot more energy, huge jump from 3 to 25. Much more energy is required because now we have to dig into the non-valence electrons. And then we could see that in the amount of energy required.